For a quick one-slide overview, deep reinforcement learning is notoriously unstable during training. Different initializations and trajectories to learning can lead to very different model outcomes and behaviors. This makes reinforcement learning hard to use. To attempt to approach this problem, we've developed a hybrid reinforcement learning and evolutionary algorithm. The primary motivation is that a population of learners would stabilize learning, because if one learner becomes unstable, it's no big deal. However, this leads to efficiency problems, so we develop methods to maximize information sharing between the population. Finally, we use ensembling as another method of stabilization and information sharing. We tested our algorithm against Advantage Actor Critic, or A2C, and found it to be more stable while maintaining similar performance characteristics. In order to see what elements of our algorithm were most impactful, we ran several ablations against different parts of our algorithm. Moving into the technical components of our presentation, we're going to start out with the architecture and training system. Our architecture consists of three neural network components: the actor networks, one for each actor in the population, the feature extractor, which is shared across all actors, which feeds into the actor network, and the value net, or the critic, which is also shared across all actors. Due to this custom architecture, a custom updating method is required. First, before the update, all the actors are given a single episode rollout to gather experiences. Starting the update, all of the individual rollouts are backpropagated through the individual actor networks. The rollouts are combined and backpropagated through the value network and feature extractor. For the shared networks, the value net and feature extractor, we batch all the gradients together and perform a single update. For the actors, a custom evolutionary process is used that will be described in the next section. We'll now go into detail about the evolutionary process for the actors and the custom operators that were used on them. We'll start with the quote-unquote repopulation method and the overall evolutionary process. For evolution, fitness is calculated by the sum of rewards during the actor's rollout. This process is viewed as a greedy parent selection process. Since we have access to the gradient, we can use gradient-informed operators to fairly confidently update the actors. Therefore, we choose only to keep one elite as a backup and use mutation and recombination for all the other actors. The algorithm is parameterized as to which parents are used to create the children, but works best when heavily skewed to the top few parents. As we said before, we can take advantage of the gradient during mutation. We call this method directed mutation. By combining the gradient step with stochastic elements contributed by a parameterized normal distribution, this method allows the algorithm to create varied actors. As we can see in the scaling figure, another property of this algorithm is that larger gradient steps lead to larger potential mutation areas, and it is best to mutate the elements with the most impact. Two types of parameter space recombination were also experimented with. After applying the gradient step, parameters were either averaged or combined through masking to create the new child. Now we'll talk about the ensembling methods used in the algorithm. The first thing to note is that ensembling is only used during test time. It is not involved during training. The goal of ensembling is to take advantage of all of the actor models that have been produced so far in the population. This can be used to further improve efficiency and stability, as one model's bad decision can be overridden by the other model's decisions. Like evolution, these ensembling methods operate off the fitness calculated during the training rollout. We implemented three different ensembling methods. The first and simplest is one elite, where we take the actions of the best actor. The one elite method serves as a pseudo baseline. The softmax method takes the softmax of the fitnesses at each step and uses the action of whichever actor wins. The weighted vote mechanism is a bit more complicated and is shown on the right. Each actor votes for an action and is given a weight based off their fitness. The action with the most votes is taken at each time step. We'll now move into our experimental setup and results. Since stability was a primary metric being tested, a fast environment is required. We used the Cartpole v2 environment, the harder one, which requires the algorithm to last for 475 time steps without letting the pole fall. For each experiment, we ran the algorithm 30 times with different initializations. For testing, we followed the standards defined by the gym. To get a test fitness, the algorithm is run 100 episodes with different environment initializations, and it must achieve at least an average of 475 time steps to be considered solved. For the ablations, we broke down and compared the elements of the mutation method, the different recombination methods, and each of the ensembling methods. To start out, we'll compare our algorithm to the baseline Advantage Actor Critic. The two main elements to note are first, when the algorithm hits 500 reward on the y-axis, and second, the area in the graphs. A larger area implies larger variance between runs and more training instability. Our algorithm was able to achieve similar solve time while maintaining much more stability across training. Next, we'll take a look at the ensembling results. While stability was relatively similar across all three, looking at the hard lines, the weighted vote mechanism was able to perform much better than the other two. Now, we'll take a look at our ablations. Weighted vote was used in all the experiments. Recombination in the top left and top right didn't greatly affect performance. We tried experimenting with stochastic learning rate, denoted as LR, and removing the parameter mutation, denoted as no param, but these had fairly small effects when compared to our baseline, with no learning rate mutation and Gaussian directed parameter mutation. We can see all the results here numerically, with the averages calculated for completion time and the areas calculated for stability. As we can see, weighted vote with no learning rate mutation but directed parameter mutation struck a good balance between stability and performance. Looking forward, a natural extension of this work is to apply it to more complex problems to see if stability gains hold up in other environments. Nowadays, the Atari learning environment is becoming the standard testing environment, but the Mujoko gym would serve as a good stepping stone considering how expensive it is to perform stability analysis. In other works, there have been effective neural network crossover methods developed. It may be good to try and attempt to use these methods within the algorithm's framework to see if more performance gains can be made. Finally, and what we believe is our most interesting insight, is the greatly reduced parameter updates. While in this work it was just a phenomenon that we observed, we wonder if this is something that could be leveraged in future algorithms, as well as the implications it makes about how stability can enable algorithms to take larger gradient steps. Finally, do we have any questions? All the code and experiment logs are available online on GitHub.